My name is Anna Bauer, and I was the chair of structural analysis at the TU Munich before, but currently I'm already working in a structural office at Mayr Ludescher Partner, so I'm right now in the transition from pure academics to the real world. So it's quite interesting. But today I will talk about Kiwi to you, and present the main ideas and how you can use it for your projects. And in order to understand how it works, I will shortly present the theory behind it. So we have Kiwi 3D. What is it? It's a finite element solver for Grasshopper and Rhino. And it allows to integrate isogeometric analysis into the CAD program. It is developed by Structure and the chair of structural analysis of TU Munich, where I was before. And it's basically me and Philip Langst, who are head of development. So we are in charge of deciding what we want to do and implement all our ideas. And we started in 2015 with this project, and the first release was in 2017. And now since then it's available in the internet since 2019. So there's already quite some time where people could work with it. So if you have some questions, you can always contact us on our website. And so finite element methods, why do we need it? So we have a physical model, but if we want to use or analyze this model, how its resistance to some loads, or can we use it in the real life, we have to do some analysis. So we generate a model and want to compute the internal stresses out of it for given loads and boundary conditions. And the classical approach is actually to take the CAD geometry and remesh it to like a mesh-based geometry consisting out of polynomials. So this is quite contradictory to the CAD model, which consists originally of NURBS. And this is the current state of the art, but it's rather inefficient and time-consuming if the mesh isn't that easy to generate. So here you can see again what's the problem. So first we have, like, for example, an exact circle, and then we make a polygonal mesh out of it. So it's becoming inaccurate. This can lead to problems in the analysis because we're not that exact anymore. And if we decide that the analysis model was not good enough, and if we have lost the connections to the CAD model, we cannot change the analysis model in the right way. So we need to go back to the CAD model and redo the whole meshing process, which can be really time-consuming. So that's the idea of the isogeometric analysis, which we will use. So we have this initial CAD model with the NURBS, and we are not meshing it on, like, for the classic approach and generate this polygonal mesh and put the degrees of freedom on the nodes of the polygonal mesh, but we take the NURBS geometry as it is and put the degrees of freedom for our structural model on the control points of the NURBS. So this is the basic idea. And with that, we can, like, put the physical simulation directly on the CAD geometry, as you can see here, and we can avoid meshing. And so we have a more efficient procedure, it's more accurate, and it's consistent. So it's not only that we use the same model for generating the analysis, but we also can use the analysis model, so the outcome, again in CAD. So there's no interruption in the process, so it's always usable. And in the same thing. So what is isogeometric analysis? So this will be a short flip through the theory, not that deep, but so you probably already know this. So you can define a curve by points, or you can do a NURBS approximation where you have 2 points outside of your curve and not on the curve again. And by moving these points, you can deform the curve. And understanding this curve type is mainly understanding isogeometric analysis. So if you understand the geometry properties, you can also do isogeometric analysis. And this is why we go a little deeper into NURBS and B-splines, which is the basis of Rhino especially. And you maybe already noticed that you can define some curves also in Rhino or Grasshopper. And for that, you need a polynomial degree. So the polynomial degree of the curve, a knot vector, which is also available in Grasshopper and Rhino. And for defining an open knot vector, you need actually p+1 equal knots at the end and the start. In Rhino, they cut off the last knot, so there you only need p equal knots to have an open knot vector. And the open knot vector has the advantage that it's interpolating the first and the last point, and the tangent is defined by the first 2 or the first last points. And these functions are also very beneficial for the structural analysis, as they have a local support. The partition of unity is always nice. They are not negative and they are linear independent, which is crucial for the analysis. And this also means for the local support. So if you move one point, you're not moving the whole curve, but only a part of it. So this is also very beneficial for just the design, because you can locally manipulate your curves and your surfaces, and not the whole surface is changing. So this is why they use B-splines in CAD, actually. You can also define multiple knots in the knot span, and by that you get some interpolating control points in between. This is quite nice for designing. In the structural analysis, we can also generate some problems with that, but I will show you that in an example later. Going to NURBS, which is an extension of B-splines. They allow you to model exact shapes like a parabola, ellipse, and hyperbolas. And what they do is they add a weight to the B-spline description. So also in Rhino, you can set a weight on the control points in order to move the curve. And if the weight is higher, the curve is attracted to the respective point. So here you can see a curve for different weights of 0.4. So if the weight is really high, the curve is almost interpolating the fourth control point. Whereas if it is 0, it's completely ignoring it. And the same principle can also be used for surfaces. There you just have 2 curves and put them on a tensor product, so orthogonal to each other, and generate by that the basis functions and the surfaces. So you need of every entity you need a net of control points, 2 knot vectors, 2 polynomial degrees, and out of that you get 2 basis functions for each direction. And the basis functions look then like this, so you have this overlap of the 2 sets of curves. And with that you can then generate the circular shapes also in 3D. The same principle could also be used for a solid with a 3rd dimension. However, this is not used in common CAD programs. So in common CAD programs, you only find surface models. There is no solid description as it is shown here. But in order to be complete, it's possible, of course. Then there is this feature, which is, refinement. And the refinement is all really nice because it's exact. So you're not changing the shape when refining. So you have in the beginning this, for example, this simple sphere with the initial control point net, and then you can do two types of refinement. So the first one is auto elevation. So you increase the polynomial degree, also possible in Rhino with change degree, or you can insert some knots, which is also possible. And the geometry, so the surface, stays always the same. However, you have more control points to manipulate the surface afterwards, which is essential for the analysis as well in order to get enough FE nodes. So, as I already told you, for the solid, there are no real solids in CAD, so what is used there is like a surface model consisting of several surfaces, and those surfaces are also trimmed, so we need to be able to deal with that with the isogeometric analysis as well. And what it looks like, you probably have seen this before, so you have the surface, and but you still have this complete control point net behind that. So you have this rectangular surface, and then you just cut out an arbitrary shape, which is visualized. So actually the whole surface is there, but only a part of it is visualized. And for the analysis, this means, so either I am able to deal with that and to be able to identify the parts where actually there is a material, or I have to remodel the plate in order to have a full surface without this trimmed out parts. So like every part of the surface is material. But this is not like a real solution, because then it would mean I have to remodel my model, because trimming is like a key feature in standard CAD. So you have to be able to do this and have to avoid the remodeling part. So we really have to go with this option here. And the second thing is also the definition of a B-rep. So as CAD models consist typically of several surfaces, we have to be able to identify the connection in between them and generate the B-rep as well. So, and this works by having the surfaces, the untrimmed surfaces, and then some curves which define the boundaries of those surfaces. And the boundaries are also used to link the three surfaces together, as you can see here. And maybe you already have used the feature in Rhino, so you have this description of the trimming curves in the UV space and also in the 3D space. So the 3D space is here, and the same curves also exist in the UV space. So going then to isogeometric analysis. So on the left, you can see the classic approach with the polygonal mesh, and the degrees of freedom are then on the nodes of the polygonal mesh. And an element is just the part in between the polygonal edges. And for the isogeometric analysis, we basically use the same, but we set the degrees of freedom on the control points of the NURB surface, and the element is defined in between the isolines of the surface or the curve. So, and the isolines correspond to the knots. So if we look back at our curve description in the parameter space, so we have one element in between each non-zero node span. And in that, there is always a constant number of control points which have influence on precisely that structural element. So if in this case, there are always 4 basis functions which are not 0. Yes, so, and for surface, it's basically the same, so you can identify the element in between two isocurves in each direction. And also generate by this the influence of the control point. Yes, and if you have this splitting into the elements, you can define for each element your stiffness matrix depending on your structural element. And each element then has a constant set of control points which influence this element, and having this matrix, you can generate a global stiffness matrix for solving your system. And then get the deformations or stresses, whatever you would like to compute. So having this general approach, you can define some arbitrary structural elements. And we at the chair had developed quite a lot in the isogeometric field. So there was a shell, and they are all also implemented in Kiwi. So there's this Kirchhoff-Love shell, a membrane element, and then a spatial beam and cable elements. And so this was it about the isogeometric analysis. So if you have any questions, you can also interrupt me, or if something was unclear. So going to Kiwi, what does Kiwi? It combines the CAD and here Rhino with the parametric modeling of grasshopper and implement the isogeometric analysis which we developed at the chair of structural analysis. And so it's fully linking IGA into CAD and also provides a pre and post-processing tool. So we can take the geometry model, which is done by the designer, and enhance it with some mechanical parameters for the engineering. So we get the analysis model, do the simulation with the analysis, and then provide some results to reuse it in the design process. So it's completely a merging of the architectural job and the engineering job. So you can work quite closely together. And we are not fully inside the CAD environment, so Rhino. So we have still an external FE solver, which is CAD. And it provides those mentioned elements and the different types of simulations. So there's static structural analysis, but also form finding and some features of optimization also not that available in Kiwi. And with the the process is basically, as I already told you, there's the pre-processing with generating the analysis model, which you have to do with Kiwi. Then put the solver on, so run the analysis task, and then decide how you will want to interpret your results afterwards. So if you want to use the deformed shape, or if you can compute some design criteria out of your results, so of the stresses or the deflections or just the curvature of the whole structure, which will evolve or something like that. So how it looks like when it's on. Can you see the video?
No, not yet. Apparently, yes. Almost.
Is it running?
Yes.
Okay, but sometimes there are problems with videos in the share screens. So we have the parametric geometry of this Ponte Musumeci, and you can adapt all the geometrical parameters. Then you can do a form finding analysis in order to find an optimal shape. So you add some boundary cables and supports and pre-stresses. You do the analysis, and then you can directly see with the same parametrization the model, which is deforming, so you can get your results back into CAD, so it's not in the FE solver. And then the nicest thing is that you can use the outcome of the first analysis in order to generate a second analysis. So you can use then the deformed form-found model to generate a structural analysis and do some computations on that. So you can generate a design and then evaluate your design with respect to structural loads or something like that. So it's basically what you want to do in your workshop. Then I would like to show you some projects which we did with Kiwi. One of the first projects was this membrane roof in Austria. Still double-checked with Sophistic, as you can see here on the plot, but all like the initial calculations were done with Kiwi, so it matched quite nicely. And then we did some more membrane projects. So this is a cladding of a surf generator, so a wave generator. It's quite cool. And the cladding was computed and form found with Kiwi. And the same for this membrane roof for the Waldstadion in Herrenberg. So yeah, that's all small optimization of the cable forces in order to get the same shape as the existing parts of the structure. And then a bigger project was, we were part of the Danish pavilion, our structure was part of the Danish pavilion of CITE and at the Biennale in 2018. So Kiwi was one part of the design process, and it was used for a more accurate analysis of the design ideas, but like a faster analysis than this extensive one with Sophistic, where you also have all the design criteria and design codes which are not implemented in Kiwi yet. So it was this intermediate step, get accurate results, but still you don't need to put up a whole structural exact model with all the design code features, things like that. And their idea was to generate a connection in between those two historic buildings, like a snake in between those. And they developed some bending active modules. So they had this knitted textile in between two flexible rods, and the membrane was then again also pulled against this string, which also bends the rods. And they developed several modules, and in the end it looked like this, the whole shape. So quite a lot of bent rods and the membranes in between. And here this is the computation of Kiwi. So you bend the rods, insert some membranes to the form finding, and then pull the membrane out for getting those cones. And this can all be done as a consecutive analysis in Kiwi. So first the form finding of the rods, so bending down, do the relaxation in order to get the correct results at the membrane. So this is then again a real geometric task. So you take the result of the bent rods, and dependent on this result, you generate the membrane, which should be in between. Then you can form find the membrane again, that it fits the shape of the rods, so also that they are in equilibrium. And then you can also form find the cones by pulling them out. And you never have to be outside of the CAD environment, so it's really a continuous workflow. And after that, you can also put some wind loads onto the structure, as the rods were not allowed to touch the historic building. So here's again the process of pulling down the shape, adding the membrane, do the cones, and then do the structural analysis. And this here is the final result, so actually quite nice, I would say. And then the most recent project, which was done at the whole structural idea was developed by Eike Schling at the TU Munich. And this is the first commercial structural type of this, with this asymptotic gridshell. You maybe already have seen those. And it's a canopy for a hotel, and has this lamellar grid in order to generate this shape of the entrance roof. And Kiwi was used for several types of analysis. So it was first of all used to evaluate if it's really possible to put those high lamellas into the shape, because if you twist them like this, you generate a lot of stress at the outer parts of the beams. So there was this analysis, is it even possible to bend or twist the lamellas in this shape? And then also you can evaluate how do I have to put them together on the ground in order to have a minimum stresses and force in the bend shape on the ground in order to assemble it. And then also you can evaluate how much force do I need in order to pull the flat shape into this three-dimensional shape. So you can see the process, and it matched quite nice the real process. So was a good experience here, and should be already in your direction, I think. So coming from the projects to the plugin itself. So here's again the concept. So you first have this geometric model that you enhance with some materials and sections and also refinement. And additionally, you have to add some loads and supports, as the geometry model does not know about it. Where is your support? And with that, you get the analysis model. And the analysis model is then sent to the solver, and by that you get the result model. And these are those categories in Kiwi. So in Grasshopper, same thing. First the geometry, then the analysis model, the solver, and the results. Then, as you will see later, there are some categories in Kiwi. We'll have a closer look at this later. And the last thing is that it's not only the Grasshopper file that is generated, but also there are some additional files which will be next to your Grasshopper file. And if you're running in some problems or want to check something, it's always good to have a look there, because there is the database with the initial model, so your geometry and your analysis model, and also the results inside a text file. And additionally, there are some other files as the error file. So if something goes wrong, it should be in this error file. And the log file, which you can also, or you see the log file running during the analysis, so you get a shell window with the log file. But if you can see everything in the log file, you can have again a look at it and analyze what what was happening during the analysis. And some last things, there are some aspects of modeling, so which you have to have in mind when you do that. The important terms are NURBS, control points, parameter space, UV or T, trimming, and the parametrization. So I'm often saying patch. So patch is either a curve or a surface. And what you have to have in mind as well is that we are using the intersection capabilities of Rhino in order to get the connectivity between different elements. So if Rhino can detect an intersection between two geometric entities, it will be coupled per default. So if there's an intersection, there can be a coupling condition in between those two patches. And this can either be overlaps or points. And also regarding the refinement, so you can draw a lot of nice shapes with very few control points. So here is not an exaggerated example, but you can draw a straight line for a cable with 2 points. But if you then want to do analysis under dead weight, it won't deform if you have supports at the ends, because the geometry cannot depict the hanging shape. So you need to add some control points for being able to represent the results with the curve as well. So you also have to think about, am I able to represent the result with my chosen parametrization, so with my control points and the knot vector, for example. So if we add one control point to the 2 points, so we have 3, we can already get the sec, but it's still not the correct result, because it's not possible to represent this hanging shape with a parabola, for example. And this is getting better and better with every point we add. And we then can approximate, with having enough control points, we can really approximate the correct result. But of course, it depends on what you would like to see. If you just want to have like a roundabout result or a really, really exact result. Because this is then also affecting the computation time, of course. So if you have more control points, the computation time goes up, but the results will get more exact. So there is always, you have to decide what is more important. And then for one geometry, there are really a lot of possibilities to model it. Especially in Grasshopper, there are like tons of possibilities, and everyone has his own preferred methods to generate a certain type of shape. But what you have to keep in mind is that for the analysis, it's usually better to have untrimmed surfaces and having a equally distributed parametrization. So not like a lot of control points in one area and then very coarse net in the other parts. Because this may corrupt your analysis. But of course you can do the analysis as well with the other parametrizations. And then a crucial part, which often generates some problems in the understanding of Kiwi. There are no units defined in Kiwi, so you decide on your units before generating your analysis node. So you have to decide for one length unit, and this length unit is also independent of the Rhino length unit. So even if Rhino has millimeters, for example, if the length is 1, it can be also 1 meter in your analysis model. So it's really, you decide before, one length unit should be 1 meter. And the same holds for force. So you decide it should be kilonewton, newton, or something else. And this defines your input and your output unit format. So if you decide for kilonewton meter, the Young's modulus has to be in kilonewtons per square meter. And the same holds also for the results. So stresses will then also be in kilonewtons per square meter, or the deflections in meters and things like that. So it's, if you understand the basics, you should be able to deal with that. And yeah, and then I think we could start with the real modeling, if you don't have any questions on the presentation. Okay.
My name is Rudy. I have a small question about one of the pictures you were showing, the final one with the asymptotic design, gridshell.
Yeah.
Just about the surface, did you model the surface from zero, or did you use a patch from a minimal existing surface?
It's actually not a minimal surface.
Okay. So you modeled the surface with zero mean curvature? No?
No, it's not necessary for the asymptotic gridshell.
Oh, okay.
You can find those light on any double curved surface. So it's around about the minimal surface, but not like a proper one.
Okay. Thank you. Just that.
Okay.
Hello, excuse me. Hello, I'm Angel. I got a question about this. Well, you said that everything was done with, well, I don't know if I got it. Everything was done with Kiwi and relaxation as well. So all the big grasshopper script that you showed, that it was separated by steps, were everything done with I guess grasshopper basics and Kiwi.
Yes.
Okay.
So relaxation, I only meant that you have the bend shape, and then you just do a new analysis with the same setup in order to like have a real equilibrium.
Oh, okay. I see.
If the analysis has the correct properties, you would actually not need it, but it's nice to have it just to be sure that the results are correct.
Oh, okay. Thank you.
Okay.
Hello. Hey, I'm Luis. And just to get super clear the concept, Kiwi does the form finding. So you give it like just as you would give it for the physics, kangaroo physics parametrization, and you give it to Kiwi, and it does the form finding itself.
Yeah, it can do some. It looks for minimal surface.
Okay.
But you can also like form finding in the broader sense that you can do a structural analysis and do bending of some rods or things like that.